All right, here we go. Section 7.3, Charles's Law. Calculate the volume or the temperature of a sample of a gas at a constant pressure. Okay, so what we're getting at here is we're looking at the law of J.A.C. Charles in 1787, which he was 41. Okay, so I'm 37, so I've still got time. He discovered that when the pressure is constant, so maintaining pressure, not manipulating the pressure at all. So imagine, doing an experiment at sea level and doing a different experiment or a comparable experiment at sea level as well. So our pressure is maintained. The volume of a sample of a gas varies directly, okay, that's a very key word, with the absolute or Kelvin temperature. Okay, so we have this direct relationship. So a direct relationship compared to like an indirect relationship would be where one parameter goes up, the other goes up at basically the same trend or rate almost. And that's illustrated with this graph right here. So what we have on our y-axis is the volume of a sample. So we've got our data plotted over here, our y-axis over here, our x-axis is temperature, so our y-axis is volume, and our x-axis is temperature. And so let's look at the y-axis. It goes from 0, 0.4 to 0.8 liters. So we're almost filling up a 1 liter bottle of Dr. Pepper. Well, as that volume increases, so too does the temperature. The temperature goes from 300 to 400 to 500 to 600 Kelvin approximately. And so that's illustrated right here as our temperature 273 to 373 to 473 to 573, as our volume increases, the ratio of volume over temperature remains almost the same. Our ratio of volume over temperature, liters over Kelvin, basically remains the same. So we see Charles's law, and we can write it as V over T is equal to a constant. And that's kind of what we saw when we were looking at our ratio of volume over temperature in the previous slide. So we were looking at those different data points. So V over T equals K, or you can manipulate that to say V, volume, is equal to our constant times the temperature. So Charles's law can also be written in terms of two sets of conditions. And this is where I was talking about maintaining a constant pressure. You can have one kind of set of data, or one experimental trial at sea level, and then do a similar experimental trial at the next at the same atmospheric pressure. Okay, so we've got V1 over T1 is equal to V2 over T2. So we jump ahead to an example problem. So this has a 678 milliliter sample of helium gas, HE, initially at 0 degrees Celsius. Okay, so I guess what I'm going to do is I'm going to go ahead and say V1 equals 678 milliliters. And while I was writing that, I noticed that my other volume is in liters. So what I want to do is I want to go ahead and do this conversion kind of on the fly. I'm going to convert my 678 milliliters to 0.678 liters. Okay, I want, I could have gone the other way. I could have converted the liters to milliliters, but the key is that I want to maintain some consistency in terms of my units. Okay, so 678 milliliters, 0.678 liters helium gas is our T sub 1 equals 0 degrees Celsius. Okay, now my question earlier was, or my problem earlier, I was looking at temperature in Kelvin. Now, temperature in Kelvin versus Celsius, I don't have to worry about changing those because of the fact that the conversion from Kelvin to degrees Celsius and back, well, if something increases 1 degree Kelvin or 1 Kelvin, it increases 1 degree Celsius. So that's a very simple relationship. So I don't have to worry about changing the units. And my question presents temperatures in degrees Celsius. So 0 is heated at constant pressure. If the final volume of the gas is 0.896 liters, what is the final temperature in degrees Celsius? Okay, you know what though? I just realized that I have 0, and when you have a factor of 0 and you're doing multiplication, that makes the entire term 0. So I'm going to convert this to 273.15k. Okay, so I'm going to set this up as V1 over T1 equals V2 over T2. Okay, so I'll write all the units, or everything that I have. 0.678 liters divided by 273.15 Kelvin. That is equal to, and this is a constant that it would be equal to, but I'm also going to make it equal to this other term, 0.896 liters divided by, well, I don't know T2. Terminator 2 Judgment Day. I couldn't resist. I had to mention it. But I can solve for it. So I'm going to say T sub 2 is equal to, and the way that I want to solve this is I want to multiply each side by T2, and I'll set this equal to, let's see, well, I'd have to put the T2 on this side too. T2. That would make it cancel. Now, I need to erase that. I'm going to say T2 times 0.678 divided by 273.15 equals 0.896. So I'll say that this T2, this is 0.00248215 is equal to 0.896. Divide each side by this 0.00248215. 0.00248215. Okay, 0.896 divided by 0.00248215. T2 is therefore going to be equal to 360 degrees Celsius, or 360.9 degrees Celsius. No, I made a mistake because I converted my units, and so now I need to convert back because this answer is in Kelvin. Now I need to subtract 273.15. Thank you very much for telling me that, Joel. This is 360.98. So 360.98 minus 273.15 equals 87.83 degrees Celsius. So effectively what this is telling us is that we have helium gas, and our volume of that helium gas is, well, 678 milliliters. Now, what we did was we allowed that gas to expand. We allowed that gas to change its volume from 678 milliliters to 896 milliliters. So it went from this confined space to a larger space. Now the key here is that the pressure did not change, and since the pressure did not change, well then our temperature had to go up. All right, well, I hope this is helpful, and I'll see you in the next section.